Hello everyone, welcome. Thanks for joining us today for this latest in our editions of the IRENA Insights webinar series. So my name is Paul Durrant. I lead the Bioenergy and the End Use Sectors teams at the IRENA Innovation and Technology Center in Bonn. For those of you who don't know us, let me very briefly introduce IRENA and our webinar series. So we're an intergovernmental organization. We've got 164 member countries and over 20 or so in the process of accession. We support our countries in their transition to a sustainable energy future. We serve as a platform for international cooperation, a center of excellence, and a repository of policy, technology, resource, and financial knowledge and data on renewable energy. Now, since our analytical work and our engagement generates a lot of valuable insights, we're constantly looking for new ways to share those insights with you, which is why we launched this fortnightly series of IRENA Insights webinars. We launched it back in January 2020, actually just before the pandemic really began, and drove a proliferation of these online events. What we're trying to do is each fortnight, presenters from IRENA's team share with you some key findings on their latest work or recent publications. And we try to give you some insights into the opportunities, trends, best practices, and innovative solutions that are addressing various challenges. Now, there's longer, deeper dive webinars out there. What we're trying to do here is keep it short and sweet, maximum 30 minutes, so we can only give you a flavor. We can't cover everything, but we hope we give you enough to decide whether to delve deeper into the topic, take a look at our reports, and so on. And we'll try and signpost you where you can find more information. Now, today's webinar is entitled Renewable Methanol, an enabler for carbon neutrality in the chemical and liquid fuel sector. Today, we will share some insights and key findings from a joint publication produced by IRENA and the Methanol Institute. That publication, Innovation Outlook on Renewable Methanol, discussed pathways to transition from fossil fuel-based methanol to renewable methanol. We talked about the market status, we explored the outlook for renewable methanol in different applications, including in the chemical and transport sectors, and we elaborated on policy actions needed to make renewable methanol cost competitive by 2050 and ideally earlier. So this timely topic is going to be presented by Mr. Xiongwu Kang. Xiongwu is one of IRENA's foremost experts on bioenergy, and his presentation will last about 15 minutes, and then there'll be time for maybe 5 minutes or so of questions at the end. Before we get to him, we've got a few housekeeping items and a bit of an introductory remarks from me. So on the housekeeping side, next slide, please. Today's webinar is recorded and will be available together with the presentation slides on our IRENA webinar website. Look under the past webinars heading. And we'll share the link with you in a follow-up email. All the previous webinar recordings and slides are there too if you want to take a look. You're all muted. I'm afraid you'll stay muted throughout the event, but we would love to hear from you. Next slide, please. So if you have any questions to Xiongwu or myself, then please send us through the questions function in the webinar software. I'll keep an eye on them as we go, and then as time allows at the end, I will pose a few of them to Xiongwu for his follow-up. I'm afraid we probably won't cover all of them, but you're very welcome to email us at the link that you'll see on the screen later on, and we'd be happy to follow up with you bilaterally if you're interested. Lastly, if you have any technical difficulties, sometimes it's better to reconnect by phone rather than PC. We haven't got any technical support available to you, but you can try the GoToWebinar website, but hopefully you won't need that. Next slide, please. So that's enough of the sort of housekeeping stuff. Let me dive into talking a little bit about the subject. But before we talk specifically about methanol, I want to give you a little bit of context on why methanol is on our agenda. Why are we talking about it? Why are we looking at it? Now, each year, one of our key flagship publications is our global roadmap for deep decarbonization. And in the context of more and more countries upping their ambition and many now committing to net zero targets by mid-century, this year's edition has focused on a pathway consistent with limiting global temperature rises to 1.5 degrees C and bringing CO2 emissions to net zero by mid-century. Now, this is a step beyond our previous analysis of a well below 2 degree pathway. And whilst the direction is the same, the pace and scale are notably larger and faster across all aspects of the energy transition. Everything really needs to be turned up to 11. Now, we published some key findings of this in March, and that's available online, and the full report is coming at the end of this month. Next slide, please. So as this little animation shows, renewable energy supply, electrification, and energy efficiency are the key components of the energy transition. 90% of all decarbonisation in 2050 will involve renewable energy in our scenario. And our analysis suggests that we have most of the technologies that we need for that transition. And we also assess that that transition is affordable. Interestingly, we've done some analysis of the leading scenarios from other organizations around the world, and there's a remarkable alignment of views now. It wasn't always the case, but over time, people have coalesced around the idea of renewables as the central feature of a deep decarbonization pathway. So there is a strong and growing consensus there. What's often stated, but I'm not sure is always fully internalized by us all, is the pace and scale of that transition is truly daunting. 1.5 degrees doesn't just mean net zero by 2050, it also means a circa 50% reduction in emissions by 2030. And to give you a little bit of a sense of scale on some of that, so by 2050, power generation triples compared to today's level, and renewable supplies 90% of total electricity. That's up from 25% in 2018. That's going to require 10 times more renewable power generation capacity. Wind and solar will likely grow to about 63% of all generation in 2050, and that's compared to 10% in 2018. On the flip side, by 2040, coal-based power generation would be a quarter of today's level and eventually would be phased out by 2050. The remaining 10% of that power generation will be supplied by natural gas and by nuclear. As you see with a big yellow block on the screen, by 2050, around 51% of final energy consumption is provided directly by electricity. However, that still leaves 49% to be addressed other ways. Next slide, please. Fuels are going to be important, therefore, and essentially we've got two low carbon routes, hydrogen-based, biomass-based, and both need to play a major role. Our scenario sees hydrogen demand growing from 120 megatons to 630 megatons by 2050. That would require 160 gigawatt of electrolyzers added on average every year between now and 2050. To give you a sense, installed capacity in 2020 was 0.3 gigawatts. So we clearly have a long way to go. Now, hydrogen's getting a lot of attention, but biomass-made fuels will also be critical. And in our scenario, biomass supply needs to sustainably grow from 54 exajoules in 2018 to 153 exajoules by 2050, with biomasses and its derivatives accounting for 18% of final energy use. Now that 153 exajoules is at the high end of ours and other assessments of what is sustainably deliverable. So one of the big challenges in this energy transition will be scaling up production sustainably, i.e. without causing social, environmental, or economic harms, and also finding ways to ensure that society can be confident in the sustainability of that biomass. Now, that's not a new insight, we've known that for many years, but the 1.5 degrees C and the net zero goals changes the urgency and scale of that challenge. And it's going to be complex to deliver that. This is a topic that bioenergy specialists spend a lot of time talking about, but there is a need for a broader discussion amongst the wider energy community and wider society, and a more nuanced discussion, and slightly balancing out that focus on hydrogen with a bit more focus on biomass. Both are needed, as I say. Next slide, please. So together, bio-based fuels and feedstocks and synthetic hydrogen-derived fuels and feedstocks will be critical for several end-use sectors, in particular heavy industry, steel, chemical sector, but also in long-haul transport, shipping, aviation. And that's where renewable methanol potentially comes in. So that's my segue to hand over to Xiong Wu, who's going to dive into how we perceive renewable methanol and its future. Xiangwu, over to you.
Next slide, please. And one more. Okay, thank you, Paul. As we saw in previous slides, achieving net zero emissions requires also huge efforts for the chemical sector. Methanol is actually a key chemical building block, thus reducing its carbon footprint is urgently needed. IRENA considered methanol as a key energy vector and tried to look at the solutions, alternatives to fossil-based methanol already back in 2013 with the biomethanol technology brief. There has been quite significant developments in this sector, and with a fast-growing interest and necessary for net zero pathway, we partnered with the Methanol Institute to explore the latest information and outlook for renewable methanol, which includes not only biomethanol, but also e-methanol. The new report was published earlier this year and available both in English and in Chinese at our website. Next slide, please. In the last 10 years, the global methanol market has grown rapidly, and the demand has more than doubled from 40 million tons in 2009 to 100 million tons in 2019, and the production capacity reached 150 million tons. The main methanol use was in the chemical production, such as formaldehyde and acetic acid, etc. But the recent growth is mainly coming from two main markets: the chemical building blocks and fuels, especially the plastic manufacturing application, so-called methanol to olefins, has grown even faster in the last decade and has been concentrated in China. Next, please. Next slide, please. Right. So methanol has three main potential applications, such as methanol for chemical building block and as fuels for shipping and fuel cells for road vehicles. Current methanol production largely depends on coal and natural gas. Unfortunately, renewable options today supply less than 1% of the global methanol production. There are two main renewable options, which were also the focus of our report and the focus of today's presentation and webinar: biomethanol and e-methanol using green hydrogen and CO2. Next, please. For methanol production, we have first the coal-based route, raw methanol, which is mostly exclusive to China, and conventional natural gas-based methanol, gray methanol. We consider the blue or low carbon methanol to be from natural gas-based methanol, but combined with the addition of renewable electricity, green hydrogen, or CO2 captured to reduce overall carbon footprint. Green or renewable methanol can be produced either from biomass or renewable electricity, green hydrogen, and renewable CO2, or a combination of those. Next, please. Globally, most of methanol is produced from steam reformation of natural gas. Around 65% of global methanol production is from this route, and the other 35% from coal. To produce methanol, natural gas and coal first have to be converted to synthesis gas, a mixture of carbon monoxide, hydrogen, and carbon dioxide. In the case of coal, syngas is obtained by gasification that combines partial oxidation and steam treatment at high temperature. A typical world-scale methanol plant using natural gas as feedstock has a production capacity of about 3,000 to 5,000 tons per day, or 1 to 1.7 million tons per year. There are also efforts to reduce the carbon footprint of methanol from fossil fuels. One option is to inject CO2 from some other process into the methanol synthesis loop. Another option would be to decarbonize the first step in methanol production from natural gas, which is the reforming step to syngas. This step is very energy intensive, requiring part of the natural gas feedstock to be burned to generate the heat for the reforming of the natural gas. Also, we can feed green hydrogen into a coal-based methanol plant to increase capacity and reduce carbon emissions, as well as carbon capture technology applications. Next, please. As we saw in previous slides, the renewable or green methanol can be broadly categorized as biomethanol and e-methanol. At first, one of the simplest ways to produce renewable methanol is through the biomethane. Instead of natural gas, biomethane can be fed into the methanol production process, which takes natural gas as feedstock. Biomethane can be obtained with some treatment from biogas produced from anaerobic digestion of organic materials, such as municipal solid waste, dairy farm waste, etc. This route has been used in commercial facilities in the Netherlands, in Germany, in the US. They use certification procedures to properly account the biomethane share in the final product. Next, please. Second route is the gasification. The production of methanol from biomass and municipal solid waste are relatively well known since they are similar to technologies used in the commercial gasification-based industry, where feedstocks are usually coal. However, the gasification aspect differs in feedstock preparation. Most feedstocks for biomethanol plant need to be homogenized in some way before being fed into the gasifier, as they come from different sources in different forms. Syngas as output of gasification is then followed by conventional methanol synthesis process. From a technological viewpoint, the key to successful commercialization of this technology is to convert the feedstock to the syngas quality required for the methanol synthesis unit. So the technology capable of generating such a high quality syngas as the used with Fischer-Tropsch for the production of various hydrocarbon fuels, including biofuels, biokerosene, etc., can be utilized also in the methanol production plants. There is an example in Canada. The company named Enerchem has been converting municipal solid waste to methanol and or ethanol for several years. Also, there are many other projects in the pipeline or operational, as we can find in the table on the right. Next, please. Another interesting type of biomethanol technology is the one coming as byproduct from pulping cycle. When wood pulp is converted for further processing into various qualities of paper and products, raw methanol is formed in the digester where wood chips react with the cooking chemicals. The methanol byproduct contains various impurities, and in almost all mills is used as an internal fuel for heat and power. It can, however, be treated and upgraded into commercial chemical grade biomethanol. In 2020, a large mill in Sweden started up operation with a production capacity of 5,250 tons per year using this technology. If such a technology is applied to all global pulp production, this would lead to 1.2 million tons of methanol production per year. Next, please. So there are a number of ways to produce e-methanol through electrochemical processes. The simplest and the most mature method is to make hydrogen through the electrolysis of water using renewable electricity, followed by catalytic reaction with the CO2 to produce e-methanol. Another approach is to produce both components of syngas, CO, and H2, and through electrolysis, and followed by conversion of the syngas to e-methanol as for the conventional methanol production. The last technology is the direct electrochemical conversion of CO2 and water to methanol, and it is also being studied, but so far only limited efficiency and yield have been achieved at a laboratory scale. The first commercial CO2 to methanol recycling plant using locally available cheap geothermal energy has been operated in Iceland at an annual capacity of 4,000 ton of methanol per year. In China, a plant started operations at 1,000 ton per year of e-methanol. This is a demonstration project, and it is the first to show the production of methanol from solar power on an industrial scale. Other e-methanol commercial plants are being planned around the world, with production capacities ranging from 8,000 to 108,000, 80,000 capacity, and overall, this would produce in excess of 700,000 ton per year of methanol. Next, please. There is another interesting concept which combines biomethanol and e-methanol production routes. So the biomethanol production has around 50% of carbon efficiency, but this hybrid process using the rest 50% of carbon with green hydrogen to produce more methanol, or green hydrogen or the oxygen from hydrogen synthesis to put it back in the methanol production can enhance the overall efficiency. This combined approach allows to lift the carbon use up to around 100%. Next, please. So we also identified some economics of renewable methanol. So compared to today's natural gas and coal-based methanol production cost, which is between 100 and 250 US dollars per ton, renewable methanol production costs in most cases are estimated to be more expensive. As you can see in the chart on the top left corner, and also the green part in the chart on the right side, the biomethanol cost is estimated at between $327 and $764 per ton. It is with a low cost of feedstock up to $6 per gigajoule, which corresponds to the upper limit of biomass and municipal solid waste commodities commercially traded in Europe and United States. Production of biomethanol from the waste streams of other industrial process offers opportunities to improve overall plant economics by simplifying feedstock logistics and also the sustainability of the product. Co-production of heat, electricity, or other chemicals has been suggested also to further improve biomethanol economics. Another option is to co-feed biomass into a coal-based gasifier or biomethane into a natural gas-based methanol plant to allow flexibility of biomass introduction and also bring down the cost of final product. Current production of e-methanol based on hydrogen and CO2 is estimated to be more expensive, approximately $800 US to $1,600 per ton, and it gets higher if CO2 is sourced from direct air capture, as you can see in the bottom left chart. The cost of e-methanol depends to a large extent on the cost of hydrogen and CO2. With expectations for cheaper green hydrogen and CO2 feedstock in the future, the cost of e-methanol is estimated to decrease to reach levels of 250 to 630 US dollar per ton. But valorization of carbon reduction potential, for example, through carbon credits, could also lower substantially the cost of renewable methanol. Compared to the production of methanol from natural gas, a decrease in CO2 emissions is estimated to be about 1.6 and 1.7 ton per ton of renewable methanol. This means that for every US dollar credit per ton of CO2 avoided, a decrease in methanol costs of about 1.6 to 1.7 dollar per ton of methanol, and that can be expected. With a credit of 100 US dollar per ton CO2, a cost reduction for renewable methanol would be 160 and 170. Next, please. So to enable and facilitate the transition to renewable methanol from fossil-based methanol, it needs a systematic investment throughout the value chain. meaning not only the technology, but also the infrastructure, supply chain, deployment, and application. Methanol is an energy vector with multiple applications. For transition to net zero world, we need to create a level playing field to facilitate sector coupling and for an optimized solution. We need to also acknowledge properly the contribution of renewable methanol to the energy sector decarbonization. The fuels have been a focus of carbon intensity, and there are many policies already implemented and also planned. But in the chemical sector, it has been seen less. Supporting market forces in the chemical sector will encourage both industry and consumers in low carbon and carbon neutral products. With that, it concludes my my presentation. Thank you very much.
Many thanks, Seungwoo. I think it was very clear. I hope our audience found good insights from that. I think because I waffled on a bit too much at the start, we're quite short on time, but I think maybe we can take one, possibly two questions at most. Keen to finish on the half-hour mark. We got a number of questions in advance. We haven't really got any in the chat right now that are directly related to methanol. There's a couple of questions there that I'll answer direct to the questioner, but specifically on methanol, if anybody wants to post anything now, then you have 2 minutes to do so. But one of the questions we got in advance, and you did touch on this in your presentation, but perhaps we can expand upon this a little bit more, is about the applications of methanol. So I should say the applications of renewable methanol. So renewable methanol can be a substitute for existing methanol use, but potentially can expand into other applications. Could you expand a little bit on what you said in your presentation on that, Seungwoo?
Yes, so the renewable methanol, actually the first application would be to substitute the current use, because in the future we would have much more demand in methanol because of the growing economy, not only for the fuel use but also for the chemicals. Like our daily products, plastics, will be growing rapidly in the future as well. So it's not only to replace the current application, but to fill the gap of current production and the future demand. So the renewable methanol can be a perfect solution to not to increase the current level of emissions, and also to decrease the emissions coming from the current applications. Also, the methanol is being considered for the fuels in the shipping sector and for fuel cells in road vehicles. But these are all the options that we should put on the table, and we cannot say we cannot pick a winner. We should create a level playing field, as mentioned in my last page.
Good, thank you. We have reached the time, and I don't see any extra questions in the chat. And I think your presentation covered the questions we got in advance of the meeting. So thank you very much, Seungwoo. That was very clear. Thanks everybody for joining us. Just a few housekeeping items to close. So next slide, please. So as I mentioned at the beginning of the webinar, we'll be sharing a link with you to where you can find this presentation and the recording of the event. We'll also share a link to a short satisfaction survey. De rigueur at the moment. We really value your feedback. It just helps us make these webinars more effective and useful to you all. So if you can take the couple of minutes to fill that out, that would be very much appreciated. We are lining several more webinars up, so do check out our website. They come every fortnight on a variety of topics. So thanks again for joining us. I hope you found it informative, and I hope you'll join us again for future webinar series. Thanks for your time.